In this video we're going to start Chapter 3, Differentiation. In this chapter you will study one of the most important processes of calculus, differentiation. In each section you'll learn new methods and rules for finding derivatives of functions. Then you will apply these rules to find such things as velocity, acceleration, and the rates of change of two or more variables that are related. For example, let me slide this up a little bit. When you're jumping from a platform, a diver's velocity is briefly positive because the diver has upward movement, but then becomes negative when the diver's falling toward the water. How can you use calculus to determine the velocity of that diver when they impact the water? And that's something we'll get to in the next section, section 3.2. So, in Chapter 3, Section 1, we're just going to look at what is a derivative and how is it related to the tangent line problem. I think I brought that up in the beginning of Chapter 2. So in this section, we're going to find the slope of a tangent line to a curve at a given point. We're going to use the limit definition to find the derivative of a function and understand the relationship between these two ideas, differentiability and continuity. But the tangent line problem. Calculus grew out of four major problems that European mathematicians were working on in the 17th century. The first one is the tangent line problem. We're going to get into that. We talked about it in section 2.1, and we're back to it here in 3.1. Velocity and acceleration problems. Those are in the next two sections after this one. And then min and max problems. Those will be covered in Chapter 4. And the other real biggie, I think calculus really come out of two questions. One is the tangent line problem. The other is the area problem. And we talked a little bit about that in 2.1 when we introduced the tangent line problem. And then we dive into that in Chapter 5. That's sort of the second half of calculus. But each of these types of problems involves this idea of a limit that we just covered in Chapter 2. And calculus can be introduced with any of these four problems. We're going to start with good old number 1, the tangent line problem. So what is a tangent line? Here, think back to geometry, we have a circle. A tangent line is just going to touch that circle at one point and no place else. It never goes inside the circle. And of course it forms a right angle with one of the radii of the circle. But when we're talking about curves, here it looks like a downward opening parabola. A tangent line at this point P is going to be sort of like the circle. It's just going to hit at one point and keep right on going. But then, if we want to find the tangent line for this point P on this odd, almost sort of S-shaped curve, here our tangent line is going to cut through our function, our graph. Here on the circle or here on the parabola, we never touch that at more than one point, and we never went through the function. Here this tangent line actually cuts through our function f of x. And then here we have another more extreme case. Here's our function f of x at this point P. Our tangent line is right here. It hits the curve once and keeps right on going, but it does cut back through the curve down here. But that's not a big deal. We're interested we are interested in the slope at a given point. Here, if we were interested in this slope, it would be at point P. Call this down here maybe point Q. If we wanted to find the slope at point Q, we would be looking at a completely different tangent line. A little word on notation here. Some people run into a nice stumbling block with all the notation and the x's and the delta x's going on in calculus. Just a quick review. F of x is x squared plus 3. Well, what if I wanted f of 2? Well, I'd just plug in a 2 wherever I see an x. That would be 2 squared plus 3. If I just wanted to change the variable, f of y would be y squared plus 3. And you're going to be seeing a lot of this. We have our value, or our x. What if we wanted to plug in x plus a little bit more, x plus delta x, some movement along the x-axis? Well, that would do basically the same thing. We would have something squared plus 3. And now in those parentheses, instead of just this x, we're going to have this quantity, x plus delta x. And then at that point we have a quantity squared. We could FOIL that out and go from there. So just pay extra attention, be extra careful around a lot of this notation. So what is the derivative at a point, or the slope at a given point? Here is on our x-axis we have this point C that we're interested in. and we want to find the slope on the curve at that point. Well, we know from Algebra 1, here's our basic definition of slope, y2 minus y1 over x2 minus x1. That's our change in y over change in x, or rise over run. But we're going to keep things pretty abstract here in calculus. Well, here is our first point. This is c, and then when we plug c into the function, it gets mapped to the curve, and then over to the y-axis. This is f of c. Now we're trying to find the slope at this point, or the slope of the tangent line at this point. Well, to find slope, we do need 2 points. So if we have this point here as c, let's move along the x-axis some amount and call that c plus some delta x. So we've moved along here to a different point. This is c plus delta x. Now if we plug that into our function, it's going to go up, hit our curve, we'll get mapped over to the y-axis, and where we had f of c down here, this is now f of c plus delta x. And now if we just focus in on the x and y-axis, here is our run, our change in x. How far did we move from c to c plus delta x? Well, that movement was delta x. Here along the y-axis, we have f of c plus delta x is up top here. Below that is f of c. Well, this is our delta y. How far we have changed or moved along the y-axis. So let's take what I have written here in blue, this slope formula, and make it look a little different. Let me switch over to red. Instead of y2, here we could think about this as x1 and x2. And then this here would be y1 and y2. Well, if we plug in our notation, this different notation, y2 is f of c plus delta x. So that's our y2 minus y1. So we're just going to minus f of c. And then our denominator, the change in x, x2 minus x1. Well, c plus delta x minus c is just going to be delta x. That's how far we have moved across the x-axis. So now we have 2 points, and we can find a slope. Here is point 2 on the graph. Here's the point we're interested in finding the slope at, our first point. So we could draw a secant line through there, right about there. But is that the exact tangent or slope of the same tangent line here at this point? No, what we want to do is we will get better and better secant lines when we make this delta x smaller and smaller and smaller. We want to sort of slide this point down the graph until it's right on top of this first point. Okay, let's see if we can get a better look at that on the Sketchpad program. Here in blue is our upper opening parabola. The function here is 1/4 x squared plus 2. So at plus 2 we have our y-intercept, and we have this upward opening parabola. We're interested in finding the slope here at point A. Point A is the one we're interested in. It's not going to move. And if we look here, it looks like it has an x value of 2 and then a y value of 3. And up here we have this other point B. This would be our x plus delta x. It looks like we added 2 to it. And then if we take that x value and plug it in, we get a y output of around 6. And here, in this box, I have the slope of the secant line. So right now you can see the secant line cuts through the parabola. It's not a tangent line at point A. But it's a good rough approximation. Now what will make that approximation better and better is if I grab this point B and start moving it more and more toward point A. And if we look here on the x-axis, right now we have a delta x of 2. That's pretty big. If I slide point B down, now watch here, the slope is 1.5. If I move it halfway there, right about here, now the slope's 1.2. It's getting to be less and less steep, and we're getting closer and closer to point A, and we can see that now we don't cut through the parabola so much. If I slide point B down more and more, here's delta x. Delta x is shrinking. Now we're down to about 3/4. Closer and closer and closer, and we can see our slope is changing. So when we get point A right on top of point B. Right now, delta x is a very tiny 0.01. Our slope here is rounded off to 1.0. See? Slide point B down, and we get a better and better tangent line approximation. When we're right on top of it, we're perfect. So maybe that helped a little bit. Okay, so we're sliding that point down. In this secant line, we're getting a better and better slope until we get it right on top, and then it is a tangent line. So essentially, the problem of finding a tangent line at a point P boils down to the problem of finding the slope of the tangent line at that point. You can approximate this with a secant line through the point of tangency and a second point on the curve like we just talked about. Blah, blah, blah. Here is the old Algebra 1 definition of slope. Here we change it to our new notation with our c's and c plus delta x's. And then we simplified it all down to this. The m of the secant line, the slope of the secant line, is this. And that's nothing more than the numerator is the change in y, and the denominator is the change in x, just delta x. And now here in the blue box is our official definition of a tangent line with slope m. And here now we are applying this idea of a limit we learned in chapter 2. Now you'll see the limit as delta x approaches 0. We're making that delta x jump on the x-axis smaller and smaller as we slide the points closer and closer together. So the limit as our delta x approaches 0 of delta y over delta x becomes this, the limit as delta x approaches 0 of our change in y over change in x formula. That's our slope. And if the limit, here it is, exists, then the line passing through the point c comma f of c with the slope m is tangent to the graph of the function f at that point. The slope of the tangent line to the graph of f at point c comma f of c is also called the slope of the graph of the function at x equals c, at that particular point. Now here in example 1, we're going to find the slope of a graph of this function, f of x equals 2x minus 3, at this given point, 2, 1. And here in the picture, we can see our graph is a straight line. Now this, we really don't even need calculus for. You know, we're trying to find the slope of a linear function at a given point. Well, the slope of a linear function is the same at any point, just because it's a straight line. But this is a nice basic example. We can introduce this idea of the limit and the new notation to figure out the slope of this, even though we should know what it is, you know, immediately. Okay, so what we want to find here is the limit as delta x approaches 0 of our quotient. And the numerator, remember, is f of something plus delta x minus f of that same something. So here, it's going to be f of, our x value is given right here in the parentheses, it's 2. So we're going to have 2 plus delta x minus f of 2, all divided by delta x. Okay, so what we're going to do is take this function and plug in x and delta x, or we can plug in for x to 2, and the delta x we're not sure of yet. So let's look at it like this. We're going to have the limit as delta x approaches 0. In the numerator, we're going to have this function, 2x minus 3. It's going to be 2 times something minus 3 minus, let me use brackets here, we're going to have another 2 times something minus 3, close that bracket off, all over delta x. So again, let's look here. I got my function as 2x minus 3. I sort of wrote it out twice, but I left parentheses in place of the x. Here it's 2 something minus 3 minus 2 times something minus 3. Now in that first set of parentheses goes the 2 plus delta x. And in the second set of parentheses is just the 2. Here is our first x coordinate right here is 2. And then we put in a second point. We jumped over here some amount delta x, so we have a 2 plus delta x. Okay, let's distribute and simplify as much as we can in that numerator. So we have the limit as delta x approaches 0. Here we'll distribute the 2. Do my divider line first. 2 times 2 is 4, plus 2 times delta x is 2 delta x. And then we have minus 3. Now here, a lot of students will forget, when we subtract that function a second time, it's in brackets, and we're always subtracting by the function, or by the formula, so we have to distribute this negative. Negative 2 times 2 is 4, so that's a minus 4. And the negative will hit this negative and become a positive, and then we'll have a plus 3, all over delta x. Alright, and now still in that numerator we can simplify a little bit more. So let's not drop our notation. The limit as delta x approaches 0. Let's just grab up all our numbers. We got a 4 minus 3 is 1. 1 minus 3 is negative 3. Negative 3 plus 3 is 0. So all that washes out, and we're left with 2 delta x over delta x. And remember, we want to apply this limit whenever we can as we let delta x approach 0. Well, this delta x in the denominator would approach 0, and we cannot divide by 0. But the nice thing here is we can just cancel that with the delta x in the numerator. So we're just left with 2. The slope of the graph at this point is 2. And again, this isn't really a calculus problem. A straight line has the same slope everywhere. We could put in point 3, 3 instead of 2, 1 and get the exact same answer. The slope is going to be 2 no matter where we look at it, just because it's a straight line. Well, let's look at one a little different now. Tangent lines to graph of a nonlinear function. So here now we have a nice parabola. Our function is x squared plus 1. The squared tells us it's going to be upward opening. The plus 1 is our y-intercept. And now we want to find the slope of not just one tangent line, but of a couple of them. We want the slope of the tangent line at this point, 0, 1, is a point on the curve. Let me put a little red dot there. So we can find the slope of the tangent line there. And at negative 1, 2. Well, negative 1 up 2, that's a point on our parabola. And we can find the slope of this tangent line also. All right. Okay, now when we start this problem, we're not going to worry about these points at all. We're just going to use this function and our x plus delta x notation and come up with a little function that will give us the slope of any point we want. So we're just going to look at, switch back over to black here. We're going to set up our limit as delta x approaches 0. And in the numerator, our function is something squared, x squared, plus 1. So we're going to have something squared plus 1 minus, and then here's where we don't want to forget those brackets, the same function, something squared plus 1, all over delta x. And remember, what we put in here, in the first set of parentheses, will be our x plus delta x. So here we're going to have x plus delta x quantity squared plus 1 minus, and here we just drop the delta x. This is just plain old x squared plus 1. All right. So we just have to simplify as much as we can. Remember, we want to apply this limit. We want to let delta x go to 0. But right now our denominator is delta x, and we can't divide by delta x. So here, first thing I'm going to do is FOIL this out. X plus delta x quantity squared. Well, that's going to be x squared plus 2x times delta x. And I'm going to put my delta x's in parentheses just to keep them straight. Plus delta x squared. Delta x squared. So I just FOILed out this first part. And now here we have our plus 1. Plus 1. Now this second part is a little easier. This is just x squared plus 1. But remember, we are in the brackets. In those red brackets, we'll distribute that negative. So when we distribute there, we're going to have a negative x squared. And then a minus 1. And that's just our numerator We have our big dividing line, and delta x is our denominator. All right, now let's check out that numerator and simplify as much as we can. So let's see what's going on there. Here we have x squared is our leading term, and here we have a minus x squared. Those cancel. Here we have a plus 1. It's going to cancel with this minus 1. So now as you're working on these problems, you're going to notice a pattern. And once we get to this point, once you FOIL things out and simplify as much as possible, every term in the numerator should have a delta x. And that's exactly what we have here. We're left with this first term is 2x times delta x plus delta x squared. Delta x squared. And our denominator is simply delta x. Now we can, before up here, we couldn't let delta x approach 0 because we would divide by 0. Now we're going to be able to cancel this delta x in the denominator out. Now be careful, I still see, even at this level of mathematics, a lot of students don't know when they can cancel something out of a numerator and denominator. Here, our denominator is delta x. So to cancel this denominator term out, delta x has to occur in each term of the numerator. And here it occurs once here, and it occurs twice here. This is delta x squared. So this delta x in the denominator is going to cancel this one out completely, and it's going to knock this one down from a delta x squared to a delta x to the first power. And our denominator is gone. Another way to think about this, some people might prefer this. I'm going to skip the limit notation. But if I look at this numerator and I factor out a delta x. So here I have factored out a delta x. What's left in the parentheses would be 2x plus delta x. And I still have my delta x in the denominator. Now since these are multiplied terms in the numerator, here I could just cancel it out like that. And I'm still left with the same result. I now have got this whittled down to 2x plus delta x. So, move that up. We'll do that again. That goes away. That's gone. That's gone. So we have the limit as delta x approaches 0. We're left simply with 2x plus delta x. Let's see here now. Now we can apply this limit. Again, we want to let delta x approach 0. Oops. So since we don't have a divide by 0 anymore, we can apply this limit. So anytime we see a delta x, we can replace it with a 0. So here our 2x is fine. That's just going to be 2x. Plus, well, as delta x goes to 0, this would just become a plus 0. And we don't have to write that at all. So here, our function, our derivative is 2x. So now back to the original problem. It says, find the slopes of the tangent line at these points. So, at point, our first point is 0, 1. We just plug in the x value here. 2 times x will become 2 times 0, and anything times 0 is 0. And then at the second point, second point was -1, 2, -1, 2. Our derivative function here, our slope function, is 2 times x, which is now 2 times -1, or -2. So let's drag the graph back down here. And the graph will verify what we found here algebraically. So at the point 0, 1 on the graph, well, here's 0 up to 1. Here's a point on our curve. The tangent line right there does look like it has a slope of 0. It's horizontal. At the other point, -1, 2, over to -1, up 2, here's a point on our parabolic curve. The slope here is this thin blue line, and it's pretty steeply negative. The slope of that tangent line there is -2. The definition of a tangent line to a curve does not cover the possibility of a vertical tangent line. For vertical tangent lines, you can use the following definition. if the function f is continuous at point C and the limit as we approach 0, delta x approaches 0, of this is equal to infinity, or it's equal to negative infinity, the vertical line at x equals c passes through this point, and that is a vertical tangent line to the graph. Here we have this odd-shaped curve. If we looked at the tangent line here, our slope would be, positive heading up this way. If we looked at the slope here, positive headed this way. But as we get closer and closer to this point C, the closer we get to that, the steeper and steeper our tangent line gets, and right on this point, our tangent line is vertical. Okay, that's a good spot to stop this video. In the next one, we'll pick up here a derivative of a function.